Welcome everyone to this week's Data Science Seminar Series. I'm David Bader and I direct the Institute for Data Science at New Jersey Institute of Technology. Today we have as our guest speaker, Dr. Tina Eliassi-Rad from Northeastern University. She's a professor of computer science at Northeastern, which is located in Boston, Massachusetts. She's a core faculty member at Northeastern's Network Science Institute. And prior to joining Northeastern, she was an associate professor of computer science at Rutgers University here in New Jersey. And before that, she was a member of the technical staff and principal investigator at Lawrence Livermore National Laboratory. Her research is at the intersection of data mining, machine learning, and network science. She has over 100 peer-reviewed publications and has given over 200 invited talks and 14 tutorials. Tina's work has been applied to personalized search on the World Wide Web, statistical indices of large-scale scientific simulation data, fraud detection, mobile ad targeting, cyber situational awareness, and ethics in machine learning. And today, she's going to be speaking on geometric and topological graph analysis for machine learning applications.
Thank you so much. Thank you for inviting me, and thank you for that kind invitation. As Professor Bader said, I'm going to talk to you guys about geometry and topology and graphs and how that's related to machine learning. Their work is funded by National Science Foundation and the Army Research Lab. And this work has been published in two network science journals since I moved up here to Northeastern, and I'm part of the Network Science Institute. When in Rome, you publish where Romans publish. And it's the mastermind of my amazing Ph.D. student, Leo Torres, and it's joint with Pablo Suarez-Serrato at UNAM and Kevin Chan at the Army Research Lab. And Leo Torres is finishing this year, and he's joining the Max Planck Institute for Mathematics and the Sciences at Leipzig to work with Jürgen Jost. So we continue this international theme. So when Leo started about 5 years ago, he came to my office and he asked, what concepts and procedures can we take from geometry and topology and apply them to mining and learning from complex networks? Complex networks, for those of you who are not familiar with it, are basically, think about the Facebook social network, that's a complex network. Think about the Twitter retweet network, that's a complex network. Basically, you have nodes and links, and the way that the nodes connect to each other forms a complex structure. And complex networks are everywhere. You can think of them from the World Wide Web to the connections in your brain, to protein-protein interaction networks, and so on and so forth. So, and Leo comes from an applied math background, and I am a graph miner. So we're like, oh yeah, let's bring these two together and see what we can learn. And in particular, we looked at two topics. One is graph distances, where, for example, I give you two graphs and you want to see how close they are. Or if you flip the coin, basically similarity and distance are the inverse relationship. How far apart these two graphs are. Why should you care about measuring distances between graphs? Imagine you have lots of chemical compound graphs and you want to, for example, cluster them. So one is clustering of graphs. The other one is anomaly detection. So for example, you're observing an email network over time and you're like, oh, something suspicious happened on Monday. To be able to say that something suspicious happened on Monday, you have to be able to measure distances between the graphs. Graph distances is a core topic within machine learning, within graph mining, but distances in general is a core topic within machine learning and data mining. And then we also looked at embeddings, and I'll talk a little bit about that if I have time at the end. So, graph distances. So what I'm going to talk to you guys about is the length spectrum, which is a mathematical construct from topology. We're going to have a detour through the non-backtracking matrix, and then I'll talk about the non-backtracking distance and some properties and its examples. And since this is Zoom and one can doze off, I'll give you the spoiler up front. So in terms of mathematics, what we found is that the length spectrum of an unweighted graph characterizes its two core uniquely up to isomorphism. So at this point, you should think, oh my gosh, this length spectrum must be an infinite mathematical construct, and it is. And so a lot of the time for us was spent on how do I actually compute this. And if you're not familiar with what a two core of a graph is, think about a graph and basically shave its dangling edges or its tree-like parts. In terms of networks, we found that the eigenvalues of the non-backtracking matrix track important descriptors of the network, such as its degree distribution and triangles. In fact, in social networks, we know that the two processes that form social networks are preferential attachment that lead to a heterogeneous degree distribution and forming of triangles, where friends of friends are friends. So these are very important descriptors of a complex network, especially if it's from the social domain. And then from the machine learning perspective, we learned that the eigenvalues of the non-backtracking matrix are a great way of measuring distance. So what is this thing called the length spectrum? We were inspired by a 2018 paper by Constantine and Lafont that was published in the Journal of Topology and Analysis, where they showed that there are sufficient conditions for the isometry of two one-dimensional metric spaces, and that isometry will induce an isomorphism. For those of you who don't know about metric spaces, think about a space where you have elements and a distance function. So for example, for a graph, the nodes in a graph are its elements, and then you can have a distance like shortest path. My apologies up front, I'm going to use the terms graph and networks interchangeably, though they are different in that graph is the mathematical data structure and a network is an instance of it that you are seeing, such as the Facebook social network. So now what is this length spectrum? So what Constantine and Lafont showed is the following. So they had this definition about the marked length spectrum of a one-dimensional metric space X, which is a function that assigns to each homotopy class the length of the corresponding minimal geodesic. And in terms of a homotopy class, just think about a geometric region in this metric space. And then you have a convex set. That convex set is the union of all the geodesic closed paths in X in this metric space. And then their theorem said that if an isomorphism preserves this marked length spectra between a metric space X1 and X2, then their convex sets are equal. And that equality, which is the isometry, will induce isomorphism up to a particular base point. And I'll talk about this base point in a minute and what it is. And so this was what was in the Constantine-Lafont paper. And what we showed is, well, what about graphs? We care about graphs, not just one-dimensional metric spaces. Well, this notion of a homotopy class is natural to graphs. Every geodesic closed path is a non-backtracking cycle where I can go to J and then not immediately come back to I. And the convex set is the two core of a graph, which again is a graph where you can think of it as I'm going to shave its tree-like parts. So here, if I am giving this graph, its tree-like parts is this guy and this guy. And so now I am, I have this after I shave the graph. We call it shave the graph down to its two core. So then the theorem that Constantine and Lafont showed, given the mapping to graphs, is that if an isomorphism preserves lengths of non-backtracking cycles, then the two core of these two graphs are isometric. and that isometry will induce isomorphism up to a particular change point. Or in a simpler English, this length spectrum, which I haven't told you yet how to construct, of a graph will characterize it uniquely up to isomorphism. That is the two core of it. And the reason being that when you talk about topology is interested in cycles and holes, and so you can't really do anything with the dangling edges. So how do I construct this length spectrum? Given a particular graph and a node, and this node is called the base point, what I'm going to do is I'm going to consider the set of all closed walks that start and end at that particular node. So I get this graph, I pick a particular node, I'm going to call it a base point, and I'm going to look at the set of all closed walks that start and end at that point. Then what I'm going to do is I'm going to group my set of closed walks into these classes, which I'm going to call equivalence classes, if the closed walk only differs by its tree-like parts. That doesn't go through the base point. So for example, in here, these two closed walks are equivalent because they only differ in this dangling edge here. So now that I have equivalence classes between my closed walks, what I'm going to do is I'm going to, from each equivalence class, pick the shortest closed walk in there. And when I now have all of my shortest closed walks, that is called the fundamental group of G with respect to that particular base point. And that is what you're seeing here. So now, as a graph miner, I don't want to go through every node in a graph. There are too many of them, and I don't want to look at that. Well, computer scientists are very good at bastardizing things. So what I'm going to do is I'm going to change the definition of equivalence of closed walks. And I'm going to say that closed walks are equivalent if they differ only by their tree-like parts, and not have this condition that they don't go through the base point. Now, if I do that, then really what I need is the non-backtracking cycles of a graph. And in particular, I would need all of them, and we'll talk about the computational aspects of that. And so now I can tell you what the length spectrum is. So the length spectrum assigns to each closed walk the length of its shaved version. So for example, for this closed walk that you're seeing, the length spectrum of it is 3. For this one, it's also 3. For this one, it's also 3. For this one, it's also 3. Okay, so now what am I assuming? I'm assuming that if you give me a graph, I can measure its length spectrum. And that if I take distances of length spectrum, that is a good distance measure between the graphs. And the reason I say that is because of that Constantin-Lafont theorem that we were able to adapt for graphs. And so one assumption is, given a graph, I can actually find its length spectrum. Finding all non-backtracking cycles in a graph is not easy. And that the distances between the length spectra of two graphs actually is meaningful and is useful for some tasks. So I have these two problems: how to compute the length spectra and how to compare them. So our solutions are to examine the output and not the inputs, and to partition the set of outputs. So what does that mean? So instead of getting a graph and finding all of its non-backtracking cycles, all I really need for the length spectrum are the counts. So what I need is how many triangles or how many cycles of length 3 there are in a graph, how many cycles of length 4 there are, how many cycles of length 5 there are, and so on and so forth. And so I don't need to actually enumerate through and output all the non-backtracking cycles of a graph. All I need is this histogram, the counts over the different lengths of cycles. So how would I compute this histogram? This is where we get into the non-backtracking matrix. For those of you who have thought about graphs and networks, you probably are very familiar with the adjacency matrix. where you have every row represents a node and every edge represents a node. And then you can have, for example, a binary if I is friends with J, or if it's a call graph, how many times I called J, or perhaps the Laplacian matrix. But now we're talking about the non-backtracking matrix. And I think the reason it's not popular so much, especially in the graph mining community, is because it's a 2m by 2m matrix. That is, if your graph has m edges, you are representing each direction of an edge in this non-backtracking matrix. And so it's a much bigger matrix than the adjacency matrix. And in general, just a rough guideline, we assume that the number of edges in a graph that has n nodes is about n log n. So what does this look like? So if I have a graph like this, then I will have a row that corresponds to the red node going to the blue node. And I will also have a row corresponding to the blue node going to the red node. And basically, I will only have a 1 if I can go from a red to a blue and the blue to the yellow. And the yellow and the red are different. That is, again, I can't come to you and immediately come back. And this is the unnormalized transition matrix of a random walker on your graph that can immediately backtrack. And as you can imagine, it's going to be an extremely sparse matrix. That is, it's going to have a lot of zeros in it. So now let's think about this matrix. If I take powers of b, let's say I take b to the power of k, and then I look at the row corresponding to edge E1 and the column corresponding to edge E2, that's going to give me the number of non-backtracking walks of length k that start at edge E1 and end at edge E2. For those of you who have worked a lot with adjacency matrices, you oftentimes will, for example, take a to the power of 2 to find paths of length 2 in your graph. So what we're interested in is cycles. So I want to start and end with the same edge. So one of the things that I can do is to find the number of non-backtracking cycles of length k. All I need to do is take this matrix B, take it to the power of k, and then sum the diagonal entries of it. Now, of course, if you remember your linear algebra, the sum of the diagonal entries of a matrix is the trace of that matrix. And I can find the trace of a matrix by just looking at its eigenvalues. So now I have turned the problem of, okay, I have a graph and I have to count all the non-backtracking cycles in this graph to, oh, you have a graph, I'm going to represent it as a non-backtracking matrix, I'm going to find its eigenvalues, and that's going to be what is going to tell me the counts for the cycles. In particular, if we go back to this picture of what I need, which is the number of triangles that a graph has, the number of rectangles that a graph has, etc., the height of each bar is just the trace of the non-backtracking matrix to the power of that length, which again, I can compute by finding the eigenvalues. So then the non-backtracking distance of two graphs is as follows. We are going to compute the cumulative density function of the respective spectral densities of the largest R eigenvalues of G and H. I don't want to find all the eigenvalues. There's no reason for me to find all the eigenvalues of G and H. And then what I'm going to do is I'm just basically going to measure the Earth mover distance between these density functions. And now the question is, this R is a hyperparameter, and how would I pick it? And in the paper, we go into depth about this, but a good choice for R is to look at the eigenvalues whose magnitude is larger than the square root of lambda 1 of the non-backtracking matrix. It has something to do with being basically able to capture a lot of the variance of what you're seeing. So then to compute the non-backtracking distance of a graph, you give me two graphs. you can give me the integer r in terms of how many eigenvalues I should compute of each graph, or I can use my heuristic to set r automatically. And I will give you a real number d, that is the non-backtracking distance between the two graphs. And the algorithm is what you're seeing here, which is I take the two graphs you give me, I shave them down to their two cores, I compute the non-backtracking matrix for each one. Usually the graph you give me is coming in an edge list. It's not going to be in the non-backtracking representation. And then I will find their eigenvalues and of the two non-backtracking matrices that correspond to the two graphs you gave me, and then I measure the earth mover distance between them. And the runtime complexity of computing the non-backtracking matrix is order O of m, which is the number of edges, plus n, which is the number of nodes, times the second moment of the degree distribution. So that's what that k squared is. Now, if you give me the graph in other forms, I can even reduce this complexity, the runtime complexity of finding the B matrix. Now, when NSF gave us money to work on this, they wanted us to look at distances that are metrics. Unfortunately, our non-backtracking distance is a pseudometric. It is not a metric. And the reason being is that you can give me two graphs and I will tell you that their distances is 0, but the two graphs are different. And the reason for this is the co-spectrality, is the way that I'm computing the number of non-backtracking cycles. So what does co-spectrality say? It says that you can give me two graphs and I will find the spectra of the two graphs. And if I measure distances based on that, I could tell you that the distance is 0, but the two graphs are different. Co-spectrality can happen on the adjacency matrix, on the Laplacian matrix, or the non-backtracking matrix. And here, Leo is showing you the smallest co-spectral graphs with respect to the non-backtracking matrix. Co-spectrality is interesting. Almost all trees are co-spectral. It's an open problem in terms of how many graphs are co-spectral. And there's a conjecture that as the size of my graph gets bigger and bigger, it's unlikely that it will have a co-spectral twin out there. So if I'm like working on the Facebook social network, it's unlikely that there's going to be another network out there that it's going to have the exact same spectra and be different. So what are some of the properties of this non-backtracking matrix that I'm using to capture distances? So one thing when you think about graphs is hubs. This is preferential attachment. When you enter a network, you want to connect to the star. And what I'm showing you is the configuration model with a parallel degree distribution. This is a graph with 10,000 nodes, average degree of 10, and the exponent of the parallel degree distribution is 2.1. The non-backtracking matrix is going to have real and imaginary eigenvalues. And so what we see is that as my network has fewer and fewer hubs, my imaginary parts go away. The imaginary parts of the eigenvalues of B go away. Which I think it's very fitting in that as your stars go away, your imaginary parts go away as well. And then in terms of triangles, what happens as my graph gets more and more triangles? Here I'm showing you an Erdős-Rényi random graph, again with 10,000 nodes, average degree of 10. And as I add more and more triangles to the graph, what happens is that this nice circle that I had of my eigenvalues around the origin disappears. And others also have found this phenomenon. So let me tell you about some experiments we did. So we looked at a whole bunch of data sets, both synthetic and not synthetic. For our real data sets, we looked at online social networks. We also looked at co-authorship networks. You may say, wait a second, aren't co-authorship networks just social networks? They are, but they're a different type of social network. So you really need to separate them from, for example, an opinions or a Twitter retweet, because the co-authorship is a projected bipartite network. So it's going to have different characteristics. We also look at peer-to-peer file sharing and autonomous systems, and I'll talk about the synthetic graphs when I show you results for the synthetic graphs. But rest assured, we looked at lots of different ones, from Barbashi-Albert to configuration model, Erdős-Rényi, hyperbolic, Kronecker, and Watts-Torres' small world models. So the first thing to do is to just do a sanity check, which is, as I rewire my edges, what happens to this non-backtracking distance? I would expect the non-backtracking distance to increase, and that's what we see here, right? So if I have this parameter, which is percentage of the edges rewired in the graph, when I get closer to 100% rewired, I'm basically not the graph that I had before. And so I would expect the distances to increase, and they do increase. Then when we look at the networks that are produced by the random graph models here, what happens in terms of their eigenvalues? So again, I'm showing you real and imaginary eigenvalues. Every dot is an eigenvalue here. The R, in terms of the number of eigenvalues that we looked at, is 200, and this is 50 graphs per model. So a model here is, for example, the Barbashi-Albert preferential attachment model, or Kronecker model, or hyperbolic model. And one of the things which is interesting is that of the random graph models that people have generated, we are not seeing eigenvalues that reside in these extreme parts. They basically are around the origin. And so then one of the things you could do is you could say, okay, I'm going to get this data, these eigenvalue data, and what if I project them, for example, by using UMAP, uniform manifold approximation and projection, and will that separate the graphs that are being generated by these different random graph models? And that is what we see. So here on the right, what you're seeing is the first component and the second component after I do my projection with UMAP. Every dot is a graph, and you see that we're able to separate the graphs fairly well. The errors are between Barbashi-Albert, Kronecker model, and configuration model. And we know that those random graph models generate graphs that are very similar to each other. So we would expect that those kinds of mistakes get done. However, still the accuracy of this separation is very high. So you can use it to, for example, separate your chemical compound graphs, etc. We also looked at heat maps to just, again, this is in a way also a sanity check, but also it shows, for example, on the right with the real graphs, in that the honest to goodness, naturally occurring unipartite social graphs are closer to each other than the co-authorship networks that you're getting. Peer-to-peer networks are really close to each other, 0 here being the distance. So the dark navy is 0, so the diagonals are navy. Autonomous systems are not as close to each other as peer-to-peer network. And then again, we see in terms of the different random graph models and their distances to other random graph models. And then this slide is basically this slide about that you need for a machine learning data mining paper, where it says, how does our method compare to other methods? And so what I'm showing you is this blue square is our method, where we automatically pick the number of eigenvalues, where the number of eigenvalues is the number that each entry is, its magnitude is greater than the square root of lambda1 of the non-backtracking matrix. I'm also showing you the our measure with where you automatically just pick 300 eigenvalues. In the paper, we go in depth in terms of experiments, in terms of the number of eigenvalues and how they change depending on whether you are working on a peer-to-peer network or a co-authorship network, etc. We compared it with methods that look at structures in the graph. As you can imagine, everybody and their top 10 closest friends have a graph distance measure. So you can't compare with everything. It's impossible to compare with all existing graph distance measures. So we only looked at ones that are actually looking at some structure in the graph. Because if you remember, for us, it's all about finding the non-backtracking cycles. So we looked at this GCD, which is a graph-lit correlation distance approach. We just looked at the top 300 eigenvalues of the Laplacian matrix. We looked at this paper by Ali Pinar et al. That appeared in the World Wide Web Conference, which is doing counts of motifs in the graph. And we also looked at this paper, which is looking at a distribution of shortest path lengths between each pair of nodes. And that way it's trying to measure distances. And what you're seeing here in terms of the results, I'm showing you homogeneity versus completeness. And you can think of homogeneity as like precision and completeness as recall. And these gray dashes are called the V-score. They're similar to the F1 score, which is the harmonic mean between precision and recall. And so higher is better. And so the blue is us. Followed by this GCD that's looking at the graph-lit correlation distance, the S measure that's measuring the distribution of the shortest path lengths, LAP, which is the top 300 Laplacian, closely followed by, if I just look at the top 300 eigenvalues of the non-backtracking matrix. This is across all of our data sets, so just picking the top 300 is not the right thing to do. And you're not seeing escape on this plot because escape had accuracy results that were below 0.5. And this is based on spectral clustering, right? So you do spectral clustering based on that distance measure, and you're trying to see how homogeneous and complete your clusters are. So to summarize this part of the talk, the non-backtracking eigenvalues are good measures for degree distribution and triangles, and you can use them to find patterns and anomalies. And for example, in the paper, we show lots and lots of results in terms of, for example, the famous Enron email data set and how you can use this distance measure to find the graphs where significant events happen, where the CEO resigned, et cetera, et cetera. And the non-backtracking distance is a nice way of measuring distance. It has some theory behind it. And the theory behind it is this length spectrum, which characterizes the two core of the graph, of the unweighted graph, uniquely up to isomorphism. The paper is at that link. And you can download Leo's code as well. So I can answer questions for the first part before I go to the embedding. I see that I have 2 comments on the chat. Oh, it's the recording. Okay, so are there any questions I can answer now for the first part in terms of the distances?
Well, I have a question. Well, sort of. I would like to ask something. Once upon a time, I had some knowledge of random graphs, and I know that there was a very interesting work that was done on evolution of random graph, where you start with just vertices, and then you change the probability of edges appearing in the structure, and there are certain places, as far as I remember, this was like 40 years ago, there is like a change in the structure of the graph itself. So at the beginning you have just edges, then first trees appear, then first triangles, which is of interest to you, appear, then you have first groupings, and then suddenly at certain probability you have this one big component with few smaller components. And it hit me that maybe if you superimpose what you are doing on this process, maybe you would capture some interesting moments, because I remember those people were really trying, for instance, to squeeze around probability 1/2 what happens, and when they were like less than an epsilon to the left and something, and then when there were more than an epsilon to the right and something. So did you try to conceptually look into mapping of evolution of random graph and what you have?
Yeah, so excellent point. So what you're talking about is there's been a lot of work done on the Erdős-Rényi graph, and when you have this connected component. So that's a slightly different problem that we are looking at, which is we're actually looking at, can I learn, do metric learning on a graph, where, for example, I know two different processes that are generating graphs. And so I would assume that the process that's generating this graph is going to generate graphs that are more similar to each other than that process. And can I use that to do metric learning? So that is one of the things we looked at. We didn't look at exactly what you were talking about. There is really nice new work by Johan Ugander, who's a professor at Stanford University, that's using choice models to generate random graph, to come up with a random graph model where a node comes into the network and makes a connection based on utility that it feels it's going to get if I connects to J. And that's based on, for example, features of I and features of J. So I would recommend that work. But we just generated a whole bunch of random graphs. This is because we know these random graph models, what features they have. And so you would like your distance measure to be able to distinguish between, for example, a Barbashi-Albert network and a Watts-Torres network. And that's one of the things that we showed. Good question. Are there other questions about the distances? If not, I'll continue on with embeddings. Okay, why don't I continue on with embeddings? What is embedding? So there's a lot of work that's been happening in terms of, I have a graph, and what I want to do is, for example, vectorize the nodes, or I want to vectorize the edges. That is, for every node, I want to have a feature vector that I can automatically extract. For every edge, I want to have that. For the entire graph, I would like to have that, or for every subgraph, I would like to have that. And actually, in the distances paper, we talk about doing edge embedding with the non-backtracking distance. Why would you want to do that? The reason being is that you know what the first and the second eigenvector of the non-backtracking matrix mean. The first one is about edge centrality, and the second one is about modularity in your graph. So unlike many of the graph embedding methods that are out there, you actually know what the meaning of the first and the second dimensions of the embedding is. And so here, for the embedding, what we did was we looked at a lot of the different methods that are out there, and we saw that basically what they're doing is distance minimization. They're saying that if you and I are close in the graph space, then you and I should be close in this embedding space. So they're not looking at the geometry of the embedding, which is to their detriment, because if I'm mapping these nodes into this lower dimensional space, there is a geometry there, and that geometry can help me in the downstream tasks like link prediction or node classification, etc. And so in terms of spoilers for this one, one of the things that we found is that there's a bijection between undirected graphs on n nodes and the n-1 dimensional simplices. Networks can encode graph structure in geometric terms using the simplex geometry of the Laplacian, and some of the most popular graph embedding methods perform only well when your clustering coefficient is high. That is, if I have a network data that has a lot of triangles, then, for example, methods like node2vec or deep walk work very well on them. But for example, if I have a peer-to-peer interaction network, then I don't do as well. And this should make sense to you because those methods are really looking for parts of this embedded space that are k nearest neighbor. And for k nearest neighbor, you need a lot of triangles. And so the method that we came up with doesn't require that. So what do we do? I'll quickly go through this. So I have my Laplacian matrix. I can do singular value decomposition that we all know and love. Now, if I zero out some of the columns in the left singular vectors and the singular values and the right singular vectors, then what I can do is I have this approximation of the Laplacian, right? And in fact, I know that the last eigenvalue of the Laplacian matrix is always 0. And so this is where now I know that I can map a graph with n nodes into an n-1 simplex. And so then really the question becomes, okay, I can take my lambda matrix and I can separate it into its square roots. Then I can absorb the square roots into the two matrices P and P transpose. So then I get my S and S transpose. And then if I look at this S matrix is giving me a vectorization of my nodes. Because every row here in this S matrix is a node. It's just that I really haven't done any kind of dimensionality reduction. Usually when people do graph embeddings, they're looking to do dimensionality reduction. And so if I have a connected graph, then this L is going to have rank n-1 with only one eigenvalue being 0. And so this S is a full rank. Or as I said, this implies that the rows of S will point to vertices of an n-1 dimensional simplex. And this was shown in a 2019 paper in the Journal of Complex Networks. But what I want to do in terms of embedding is not use all the n-1 dimensions, but just use d dimensions of it. And so the question then is, how do I pick d? And this is just a picture of the graph Laplacian, the geometric Laplacian Eigenmap embedding, where if I have a graph that has 3 nodes, then it can be mapped to a 2D simplex triangle. And here is the embedding of these 3 nodes in this 2D space. If I have a graph that has 4 nodes, then I have a 3D simplex, and then this is the embedding in a 2D space. Obviously, it gets harder to show it in larger dimensions. And then if I have the famous Karate Club network that has 34 nodes, that maps to a 33-dimensional simplex. And these are the vectors corresponding to the nodes. So then, one of the things that people use these embeddings is to do graph reconstruction. So given this S matrix that I found, right? So I started with a graph, I found its Laplacian, I did singular value decomposition, I took the singular value matrix, I separated it into its roots, I merged the roots to the side matrices, and then I said, oh, here's this S matrix, and I'm only gonna look at its D columns, and that's gonna be the embedding of my nodes. And so the question is, how would I use this S matrix that I have now to reconstruct a graph? And this is, you can think of it as like link prediction that a lot of people use. Now, if I didn't do any kind of dimensionality reduction and the number of columns of S that I picked is n-1, then all I have to do is take S and multiply it by its transpose, and I will get my Laplacian matrix, and then I'll be good to go. But if you don't have that, then you have to find this threshold theta. And you can find this threshold theta, for example, by doing a Gaussian mixture model, or, for example, kernel density estimation. In the paper, we talk at length about the different methods to find this theta. And of course, in your graph, you're going to have a lot more non-edges, 0, than edges, which is the -1. And the -1 is because you're dealing with the Laplacian. So then we looked at this graph reconstruction. What you're seeing here is I'm showing you for a protein-protein interaction network. Protein-protein interaction networks don't have a lot of triangles, unlike, for example, a co-authorship network or the Wikivote network. And so on the x-axis, you're seeing average clustering coefficient. Average clustering coefficient is computed as follows. For every node, you look at the number of triangles around the node over the possible number of triangles that that node can have, and then you go through all the nodes in your graph and you take the average of it. And so you see here that in a peer-to-peer network, it's very low average clustering coefficient, versus in a co-authorship network, it's very high. On the y-axis here, you're seeing the number of dimensions. So how many columns of the S matrix would you pick? I'm showing the popular node-to-vec graph embedding, which does a random walk on the graph to find context around every node, and then does a word embedding by using a skipgram. I'm also comparing with Laplacian embedding, and the green line is SDNE, which is a deep network autoencoder approach. And one of the things that we see here is, if you look at when I don't have a lot of triangles, then GLEE, which is the red line, is beating the other lines. The y-axis here is precision at k, that is how many of the edges at, for example, top 0.5 times 10 to the 4 that I get. And then as triangles are added, then I do better. And so here we see that our performance, so the GLEE's performance increases as dimensions increase in your embedding and the clustering increases. And so we can construct, for example, 10,000 edges with almost perfection in these charts. The other one the other task that is used a lot for these embeddings is link prediction based on common neighbors. And so if I have a social network, then usually the number of common neighbors is an excellent predictor of whether I will have a link to you or not. This is triadic closure. In fact, if there are two people who have lots of common friends and they're not friends, then there's a reason behind it, right? Because they have had so many opportunities to become friends and they did not. So then if I want to find out if two nodes I and j are friends after this mapping, then all I need to do is I need to find the centroid of the set of nodes that are common to them, and then look at the angle between the I and j to that centroid. And then if I have graphs that have low clustering, and this was a recent paper, actually, I think now 2 years ago by Barabashi lab, that said if you want to do link prediction on protein-protein interaction networks, you should actually look at paths of length 3. And so we can easily do this by, so if I want to know if like one protein is interacting with another protein, by taking the degree of one node, degree of the other node, looking at the centroid of the neighbors of I and the centroids of the neighbors of j, and then looking at the common neighbors between them and the length of that S, of the S vectors of the common neighbors. And here is the link prediction results. Again, obviously, as dimensions increase, one does better. So these are the dimension in terms of the number of columns, let's say, of the S matrix. Again, I'm showing you as the average clustering coefficient changes. And then on the y-axis, I'm showing you AUC area under the RC curve. Higher is obviously better. And so we see, for example, here, node 2 vec, even with 2 to the 9, it does extremely poorly in terms of link prediction for a graph that doesn't have a lot of triangles. Versus like for us, so this is the red line is GLEE, where I'm computing the link prediction based on this this equation. We're doing very well. So just as a summary, there is a bijection between undirected graphs and simplices. We can encode the graph structure in terms of geometry. And one of the things that GLEE doesn't do is it doesn't make any assumptions about the graph structure. So we're not assuming that I have high clustering coefficient or I have high triangles. And then you can download the paper and the code there. The paper appeared in a Journal of Complex Networks. And that is it for the embedding. I'm happy to answer any questions about the first part or the second part. Sorry, I'm trying to go to the slide. Go ahead. Any questions you can answer?
So if folks have questions, that can put them in the chat or unmute and ask. Maybe I'll ask a question about the embedding section, where you're looking at graphs that typically come from social networks or similar types of networks that grow over time. How do the embedding measures change, or how robust are they to changes in the graph if you look at a dynamic graph over time?
Yeah, excellent question. So there are people who have looked at temporal graphs. We haven't looked at temporal graphs. The biggest thing is, again, the general idea is that if I'm close to you in the graph space, I should be close to you in the embedding space. That's where the majority of people assume. So then the question is, how close am I to myself in the previous time versus me to my neighbors now? Right, and so you have to be able to somehow resolve that conflict, and like how far are you from yourself like 2 hops ago? And so there are people who have worked on. You can think of this as like multi-layer networks, or you can represent it as a tensor and factorize the tensor. In a sense, that's the embedding, right? And so we haven't looked at that. Others have, and I don't. Off the top of my head, don't know what exactly they found. The one thing is that as computer scientists, we oftentimes don't model time continuously, right? We tell you, do you want it fast or do you want it good? And you want it fast, so I'm going to discretize it. And then the question is, how do you discretize it properly? How do you discretize the edges properly? But I don't know many people have looked at it in terms of over time. There's a few people who have, but not that many.
Have you looked at these metrics, and for instance, as graphs get larger and larger, are there any limitations on how well the method works if you're looking at, say, a trillion vertex graph versus a 50 vertex graph?
We didn't optimize for a trillion node graph, or even even a million node graph. So for the first part with the graph distances, right, you have to put together the non-backtracking matrix, and then you have to find its eigenvalues. Now, if there is a faster way, maybe through sampling, that somebody can give me that histogram, then I'll be good to go, right? But as you know, like finding structures in a graph is notoriously expensive computationally. Like if I just sit down to think about, oh, the number of non-backtracking cycles in this graph, both simple and complex, right? That would be very difficult. So we kind of push that off to people who do HPC, right? Folks like you, like if you find this interesting, it's like, okay, well, how would I put together the non-backtracking matrix? And like, given that perhaps my non-backtracking matrix will be some approximation, how much off is it gonna be? And then finding the spectra of it. Now, having said that, just one thing is that if I find the number of non-backtracking cycles a different way, then perhaps I will have a metric, right? The reason the non-backtracking distance that we have is not a metric is because of the way we're computing the number of cycles.
Right. So another sort of observation or question in, I believe it was the distance metric part of your talk, you looked at the non-backtracking matrices and evaluated them as you did these random rewirings. And that reminded me of the notion of modularity and really looking at the difference between a graph and its randomly rewired version. So is there some connection to modularity that you've thought about in this work? You know, the robustness of the method?
Yeah, so very, very good question. So actually that work was by Mark Newman, was the senior author on that work, where basically it's like, how much should I believe the communities that I'm finding, right? And so if I were to rewire the graph, there's this notion of value of information, right? So how many bits do I need to store the communities of the original graph? Now I rewire it, and how many bits do I need to store the communities of the rewired graph, given that I have done some modifications to the graph. We didn't look at it in terms of robustness to attacks like that for the distance. In other work, we are looking a lot at adversarial learning on graphs. So for example, if I want to do targeted diffusion, right? So I have a network and I want to get to your mail server, right? The machines on your mail server. Like, how would I attack that that subgraph without having you find me, right? As an attacker, what can I do? Or like, for example, what we're calling man-in-the-middle attack, where I want communication from A to B to go through my path or go through my edge. And then like what the attacker can do is cut edges or like drop packets, right? And it's interesting because, like, for example, in the man-in-the-middle attack, if the attacker can cut edges, then that problem is NP hard. But if the attacker can, because it reduces to basically vertex cover, if the attacker can basically fiddle with the weights on the edges, so as packets are going through, like I won't send all the packets or I'll add more packets, then that's NP. So lots of fun things in terms of adversarial attacks on machine learning. The one thing that seems to be coming through is that if you learn your machine learning or do your data mining on the lower rank representation of the graph, then your machine learning or data mining algorithm is going to be more robust. And this has been shown by many different people, including Vagelis Papadakis at UCR. So take your graph, find a low rank representation of it, then do machine learning and data mining on that if you're worried about adversaries.
Got it.
Yeah.
So are there any questions from any of the audience? Okay, so Tina, thank you again for a wonderful talk in network science and machine learning. It was a really nice presentation. I learned a lot, and I appreciate you joining us in this very international audience today. So thank you again.
Thank you for the invitation, David. I enjoyed being here, and thank the audience for their attention.